Welcome to the Cloudify Tech Talk Podcast, taking a deeper dive into all things DevOps, all things tool chains, all things automation, and all things orchestration.
Guys, welcome to a super special edition of the Cloudify Tech Talk Podcast. My name is Johnny. I'll be your moderator. Basically, in this session, we are going to be taking a awesome deep dive into machine learning, into AI, etc., when it comes to DevOps, with a very special guest and a very special use case, if you will. To reveal the special guest and to talk a little bit more on the intricacies of the session, I'm handing off to Nati Shalom, our CTO. Nati?
Excellent. Thanks very much, Johnny. And Josh, welcome to the podcast. I think we spoke a couple of weeks ago about the topics, and I was kind of overwhelmed with the background and history that you brought in. As Johnny mentioned, the topic for this discussion is going to be very much focusing on AI and machine learning, kind of pretty hot topic these days. But I thought that, your background and history, I think you started very early on when you were young in the entrepreneurship kind of journey, not necessarily with AI, but I thought that a quick introduction to yourself and your background would probably set the stage for the discussion before we jump into everything AI and everything machine learning. So Josh, go ahead.
All right, thank you very much. I appreciate that. So my name is Josh Odmark. I'm the CTO and founder of Pandio. I started my career very early. I started a company back in the early 2000s with somebody that I met online, which was not a very common thing back then. As a senior in high school, and that company took off and kind of made me think that being an entrepreneur was easy. But we made like $16,000 in the first week of running the business, and ended the first month with $50,000 in revenue. So it was like a wild ride for me. We basically ran websites that were very popular. They received between 500,000 and a million unique visits, which in the early 2000s was quite popular websites. So that sort of kicked it off and sort of got me a really good sort of introduction into high volume data and what that sort of looks like. And ever since, I've been kind of a serial entrepreneur since then. Raised $1 million to start a classified ad company. Also worked on a lead generation company out of south of Florida. Both those companies, the classified ads was sort of hyper local ads. So you could think of like a Craigslist competitor with the sort of component where when you list a classified ad on the website, it would place it on third-party websites to sort of give you additional exposure. That was the whole pitch. And the lead generation company was very interesting because this was in the late 2000s, around 2009, and our whole sort of angle was real-time bidding on leads, which was kind of a relatively new idea. So all those sort of experiences taught me or sort of put me into the deep zone with a whole lot of data and real-time data. So fast forward to recently, and I'm working on a hot startup out of Santa Barbara, California called Carpe Data, and they help do machine learning and AI for major insurance carriers. And after that,
so maybe just before we jump into Carpe Data, just to kind of summarize your entrepreneurship experience, which, as I said, is pretty interesting, especially given the age in which you started in high school. For those, again, who are less familiar with Craigslist, think about it as kind of a simplified Yellow Pages and whatever, very popular in the US and probably elsewhere. Not everyone realized what it means, but I thought that, kind of the intersection that I think I've kind of read through your experience was not just, dealing with the technology side of things, again, dealing with massive data, but also how to make business out of it, which I think is pretty interlinked with your history. And at that time, that was page ranking, that was, you mentioned the ads, and other things that I think, again, those are familiar with the Google history, that's kind of pretty much how you make money out of data at the time. I think that's kind of the way to look at that. So that's an interesting intersection between entrepreneurship, technology, and finding a way to make money out of data, which I think was very, very early on at the time to do those type of things. So that's kind of a quick summary of the introduction section. Let's jump again into 2017. By that time, what age are you?
Oh man, make me do some math here. So yeah, 2017, I was 34 years old by that time.
Okay.
Yeah, so
still pretty young.
Yeah, I suppose. It's like when I hit 30, though, I felt like I was no longer young anymore. It's like your body sort of it tells you can and can't do certain things anymore. So, but yeah, I was 34 when I joined Carpe Data.
Yeah, actually, I can tell you out of my age, which is a little bit further than yours, that at least for me, the 30s is where I felt the oldest in my life. And I'm always saying, because you get the mortgage and you get kids and you get family and you get new startups and careers and all those things kind of pile up all of a sudden, you're kind of coming almost out of university with a pile of duties on your head, and it just buries you. So that's really the time in which I felt the oldest in my life, and ever since I'm feeling younger every year. That's kind of at least I like to think about.
Well, I love to hear that, because I just had my first.
That's my mantra.
4 weeks ago. Yeah.
So wait a couple of years. I think Elon here can share some of his experience here, especially when we're talking about the time of Corona and the time in which we're doing working from home. Elon is the is the heavy duty here in terms of trying to maneuver kids over Zoom sessions. So that's
nice.
So you can sympathize with you. So good luck with the newborn, by the way.
Thank you.
So I think that's a great introduction to Carpe Data. So why don't you take us through your 30th?
So I joined Carpe Data as employee number 6, and so they were very small company. The beauty of the positioning that they were in is they had a lot of very strong contacts in the insurance space, and they were interested in me because at that time I had sort of a lot of experience with growing sort of startups when they sort of either have an MVP or are working towards an MVP, and they're sort of skyrocketing. So kind of on your traditional hockey stick graph of growth. I was very good over the last 10 years or so at helping companies make that transition from when you've got a couple customers to when you can't service the customers fast enough. So that was my specialty, and that was one of the reasons why they were very interested in me. So they hired me to run their engineering department. So I built out kind of your traditional, engineers. This is in the insurance space. So we had actuaries and data analysts and things like that. And their whole angle was to help the insurance carriers use other types of data in their machine learning and AI for the purposes of predicting risk. So that was it's a very fascinating position. So that's things like using social media data, Facebook, Twitter, et cetera, pretty much anything public available on the internet. We would help corral and then clean and then sort of help them learn things from that. And so I grew that team to about 30 individuals on the technical team before I left to found Pandio. And that particular project was very interesting because we were sort of getting into the space of massive amounts of data. I mean, these insurance carriers, they have so much data, it's absolutely ridiculous. And they're sitting on huge amounts of data as well. For example, one of those large insurance carriers had satellite imagery of the entire United States just sitting on a cluster of servers. So that was hundreds of petabytes of data. So that's just one example. They had data about nearly everything you could imagine, because these big insurance carriers, they're in every industry. They're insuring and doing things like that. So they basically were opening up the kimono to us. So, I mean, it was a wild sort of position to be in. They would pay us large amounts of money and say, here's a huge amount of data, try to find some patterns in it. So that was, I mean, it felt amazing, because you're just sort of sitting back, and it's kind of, they've asked you to do something that's not very specific, but it's fun because you now have this huge amount of data, but now you got to figure out to do things with it. So that's when I sort of started to dive into the sort of DevOps nature of dealing with a huge amount of data and doing inference against it. At that particular time, I wasn't too familiar with data science, but I was very familiar with how to sort of deal with huge amounts of data. And it was at that time that we hired Adam Tashman, who is a PhD in data science. He taught at the University of Santa Barbara. That was an incredible sort of experience for me, because this is a person that understands all the intricacies of data science, the algorithms, how they work, what it's all about. And of course, a fair amount kind of goes over your head, but I was sort of tasked with bringing it all together. So, I had to sort of coordinate with the product team to figure out what was going to be built. I had to coordinate with the tech team on the actual tech choices, more like an architect would. I had to work with the data science team, which is all new to me, kind of their sort of processes and how they need the data and how they need to do training, what it looks like to allocate servers to them to do that. So it was quite a crazy ride. And what we sort of found in there was we tried using all off-the-shelf solutions to move data. And what was very interesting about working with the insurance carriers is sometimes you could use the cloud and sometimes you couldn't. So that created very interesting situations. So sometimes you could move the data, sometimes you couldn't. Sometimes you had unlimited CPU resources, and sometimes they would only allocate you a certain amount of virtual machines. Sometimes you would have GPU instances and sometimes you wouldn't. So you're sort of trying to solve these problems with, sometimes significant constraints and sometimes not. But what we sort of found is we tried to use off-the-shelf solutions like SQS and Kinesis and Kafka for the logistics of data, and found that to be very difficult. When you're sort of, imagine hundreds of petabytes of data, we were getting
just again, just to make sure that everyone would follow what we're discussing here right now. So basically, when you're describing SQS, it's the Amazon messaging systems, and Kafka, obviously, it's an open source project for doing messaging, Apache project. And when you're saying that you've tried to use SQS, you've run into some limits. Can you elaborate on that a little bit?
Yeah. So when it comes to logistics, you need some sort of ability to sort of
again.
coordinate.
I'll stop you for a second again, just again for the audience to make sure that they follow what we described. So when you're saying logistics on data, that's usually involves how you get data from the data source and then put it into some sort of a queryable kind of service where you could actually do something with that data, right? So if you can, say a few words about that logistics aspect.
Yeah, exactly. So, logistics is just sort of the movement and storage and connectivity of data. So think it like, the plumbing of a house, like it's actually just the pipes of moving things around. So we had sort of to figure out how to move sort of large data sets like that. And so specifically with SQS, the thing that you don't really realize until you use things like this at major scale is the latency is very slow. And then you start to run into sort of phantom limitations. So I say phantom because if you dig deep enough, you can sort of find them where somebody talks about how they sort of hit this limit and had to reach out to AWS support. Now, I would say out of everybody, AWS is the best, but you'll get things like sort of connection limits. limitations on the number of messages and things like that. But by far the biggest issue with SQS was connections, like the actual physical client that you open a connection to SQS to use it, and then the latency, which makes total sense. I mean, if you're Amazon, you've got this service SQS, you're serving it up to a huge amount of people. You're sort of building it for middle of the road or the averages. So you look at how your entire customer base uses it, and then you sort of make it performant for that upper average. But for us, being sort of a heavy user in that sort of case, that's not really something that they expect you to use SQS for that. Now, again, since AWS was a first mover, they're a lot better than that than, say, somebody like Google. Google's notorious, the Google Cloud, for having terrible support. And to me, it's been so bad that we just have not been able to use Google for certain things, because when you hit a limit, they are not very helpful. There's nobody you can call. But with AWS, they have really great support. And so another couple issues we ran into using AWS, which was we were using their I forget it's like their Postgres database, and so we were using that almost. You could think of it like, what was that? Yeah, RDS. So, so they have that that new service. Well, it's not really relevant, but so RDS has limitations too, and you can get into a situation where, I mean, anybody that's sort of dealt with DevOps, sometimes when you use things a certain way, your indexes start acting weird, and you need the ability to get to the underlying system to sort of figure out what's going on. Was it corrupted? What happened? Am I using it wrong? But when you use kind of hosted solutions, you're sort of limited in doing things like that. So you inevitably, with these large systems, need to get closer to the bare metal to sort of troubleshoot them and figure them out. But by and far, the biggest issue with sort of cloud services is the latency. As an example, a leading sort of competitor to SQS, you can expect like 10 millisecond latency. And with SQS, you see typically between 200 to 500 millisecond latency. And when you're talking sort of massive scale, like you're trying to churn through 100 petabytes of data as fast as you can, that sort of latency really becomes a problem, because you're paying per hour of usage. So, a 10x slowdown is significant at those types of scales. So that's kind of our experience with the cloud. Then we sort of moved into more homegrown solutions like Kafka and things like that. The sort of issues we ran with Kafka is things most people are familiar with. It sort of doesn't scale well horizontally because topics are tied to brokers. And so then you can sort of really only scale to a certain point vertically. And you can only have a topic sort of that can work as like tied to the biggest hard drive you've got type of a thing, because they don't separate compute and storage. So there's just technical limitations there. And due to the nature of how they structure their architecture, you can't use a whole lot of topics. So we found Kafka to be fantastic up to a certain point. So it starts to sort of break at the seams based on your volume of traffic. So that might be a million messages a second through a topic. But when you sort of start to go above that, which is the way we see things trending right now, most people are doing things that are analytical in nature. And there's really no huge need kind of from a throughput standpoint. But when you get to AI and ML, because it's not as linear in nature, when you think of like an analytical pipeline, it's sort of linear in nature. Something comes from the left, moves into the system, maybe it gets transformed, you're doing some calculation on it with something like Apache Flink, and then you're storing the result in the database, which powers a dashboard or a BI tool that a human sort of looks at to get a better understanding of your business. But when it gets into the ML and AI nature, that's all automated past when you have your results and looks like a circular feedback loop. So, instead of something getting put into a database for a visualization or a human to look at, it goes into a model. The model spits out an inference or a prediction value, and that feeds into another model, which then the output of those models eventually gets put back in the beginning of that pipeline, the linear pipeline. So it looks like a loop.
Yeah. So again, let's do a pause for a second just to make sure that I capture all the things that you mentioned. So we started with the logistics of the data, and logistics meaning shipping data from the source into the actual data system. You mentioned trying to use any of the cloud services at the time that was SQS. The issue there was latency and some sort of a predictive behavior or deterministic behavior, especially when it comes to scale. I think by large, you mentioned that the services on Amazon is pretty advanced and the support is great as opposed to Google. Again, at the time, I'm assuming that things have probably changed since then, but we're talking about 2017, I think, right?
That bridges. That bridges into late 2018, but yeah.
Okay. So that brought you to use a homegrown solution based on Kafka. So people are less familiar with Kafka. Apache Kafka is an open source message queue system. Don't remember the exact time it was launched. And then you mentioned a couple of things that I wanted to elaborate, if I captured it correctly. The scaling of Kafka. So you mentioned the limit of topics, and then the ability to scale horizontally beyond topics, which was also limited. So for those who are less familiar with those topics, I'll just kind of explain what Josh was trying to say. So basically, the way messaging system is structured is in a way in which you have queues, and queues are needs to be ordered, and in order that they would need to be ordered in a timely fashion, kind of a FIFO kind of model, they have to be in some sort of a server. Usually that's kind of how the data systems are structured. That's the easiest way to order messages in a consistent way. Yeah, but that also limits the scale. So if you have a topic that needs to have, so they scale well between topics because each topic can live in a different server. But when you have a massive amount of data on a certain topic, that's kind of where you hit the scale limit, and therefore your option to scale is scaling up, meaning increasing the server capacity and not by adding more servers, which is, I would say, more a better way to scale in the cloud kind of space. And that's one limit of Kafka. And then you mentioned that even in you had an issue also with the number of topics that you could also scale. If you could elaborate on that, I'm not sure that I captured that point well.
So just the way that Kafka's architecture is sort of designed, and here we're sort of running up against my sort of expertise of Kafka, because from my perspective, I'm always the sort of like CTO figure. So for me, sure, I've got to look at the sort of whole tech team holistically and understand sort of limitations across the whole thing. But just due to the nature of the architecture of Kafka, it doesn't support using hundreds of thousands of topics. So it has a sort of limit of tens of thousands of topics. So somehow the way it's sort of designed and the way topics are set up inside of Kafka, it doesn't play nice when you have lots of topics, and even tens of thousands stresses it out. What we see most people is they stick to less than 1,000 topics. It is sort of a loose guideline generally of Kafka. And depending on how you architect something.
Yeah, and that resulted in some cost issues, right? Because you had to over provision things, if I recall correctly. And do all sort of things that are related to that. Yeah.
Exactly. So that right there is the biggest negative of Kafka. So due to the nature of it, so when you sort of scale up and then you want to scale down, it has to rebalance data across the topics. So it moves your sort of topic and such. It has to rebalance the data. So that means that traditionally, when your data is smaller, that's easier because it's just a computation at the end of the day. Like it's just reorganizing data. Imagine if you were to move data from one queue to another queue. It's similar in nature to that. So it's not overly complex, but it just takes time. But imagine you had huge amounts of data. So millions and millions of messages. So that just takes time. So what you typically see in the wild is people over provision for Kafka. So they look at their usage graph and they look at the highest point of that graph, the most it needs to support at any one time. And then they provision 10% above that. When you get into sort of machine learning and AI and things like that, that sort of usage graph looks way crazier than traditional event streaming, pub sub, or queues. So because what it looks like is you might have a team of data scientists that read in 3 years of data and then need to sort of process it and use it for something. Then you might have another team that does the exact same thing. And that's in addition to your normal usage. And pulling 3 years of data, I don't think I need to stress how like massive that could be. So that creates a huge amount of stress on your logistics or messaging platform. So then what we ended up doing was, since we're doing machine learning and using it as like a pub sub, like event streaming, so it's almost like just coordinating messages versus a queue scenario. We had to create a massive Kafka cluster. And since we were training typically every couple days, it was a huge pain to sort of scale it back down. So we just left it up. So it's this huge expensive cluster that it doesn't make sense to scale down because it's too painful. So that's a big thing.
You touched on training. Can you elaborate what training means again for those who are novice to that topic?
Yeah. So that also is a good transition into sort of the way people are doing it differently today. So traditional machine learning, you do what's called like a batch training. So you have a finite data set and you need to grab that data set and have it in hand. And sort of process it to train an algorithm. So training is basically, it ends up looking like a big matrix at the end of the day. So if you've got 1 million records or 10 million records, imagine those as columns of a matrix. And then your training it's performing a mathematic calculation on each cell of the matrix, and it's putting that calculation into the second row of the matrix. And then it's doing another calculation on that second row. So it's doing it 1 million times or 10 million times. And then it keeps going down the matrix. Those are typically the layers of your training. So that's what machine learning looks like at the end of the day. It's just turning letters into numbers and doing some calculation. And then where it gets really interesting is when you've got that sort of matrix, the machine learning has the ability to do backward propagation. So it can go back. If it's on row 5, column 50, it can go backwards or it can go forwards. So that's why it's important to have sort of a finite data set in hand so that you can go backwards through it or forwards through it. So you can just imagine a cursor going forward and backwards through, a data set. Pretty straightforward. So to do that, imagine huge amounts of data. Typically, the more data you have, the more accurate your machine learning model is after you've trained it. So that's its ability to predict the future is more accurate with more data you have. So all those math calculations, something has to coordinate that. Something has to say, okay, I need to do these 10 calculations. I'm going to send it over to this microservice or this process to do that. So all that gets very heavy in the logistics nature of computing. Does that sort of clarify what that is for you?
Yeah, definitely. And this is where, people are hearing, continuously on GPU, NVIDIA, and those sort of things. Why is that even important when you talk about those topics?
Yeah, so what's interesting is GPUs were built obviously to render graphics to a screen, and the nature of how it does that is basically math with like over matrices when you actually like look into how graphics are done. So GPUs were never built for machine learning. It's kind of one of those things where just due to the nature of how they work, they're a shoe-in for machine learning. They just perform it much better. It's not like very little, it's orders of magnitude better. Whereas a traditional CPU, it has sort of limited cores and it works as a sort of queue of things to do. So your computer is constantly switching between things to do over like 4 to 8 cores for a traditional, desktop computer. Well, if you think of like an NVIDIA GPU, a traditional one has 2,000 cores. So the cores aren't the same. It's not like a GPU is way more powerful than a CPU broadly. They're different cores. They're smaller and they're sort of functionally different. They're more parallel in nature. But that just is sort of why GPUs can sort of do matricey math more efficiently than a CPU. A CPU kind of walks through it serially in series, and a GPU can do that more in parallel. So you can sort of train a model on a CPU and a GPU, and the GPU will just finish, 2 orders of magnitude sometimes or more faster actual time to get to the end of the calculations.
Okay, so again, pause here for a second, just to again make sure that the audience following what we're discussing here right now. So I think what Josh mentioned is that the reason why GPU became popular, GPU was originally designed for graphic analytics, so graphic processing, and that's kind of where NVIDIA came in. The nature of graphics is obviously you take feeds of graphs and data graphs and need to present it on a screen in relatively fast model, and the architecture that they built is highly parallel to do that, so that they can actually process a lot of those signals in very timely fashion. Where a CPU was really built for do more transactional work, which is, as you mentioned, orders of command that are basically done mostly serially, and the level of parallelism was actually introduced very recently, like in the couple of years, where we have a multi-core architecture, but still the way it lends itself less to highly parallel type of architecture, but more to more sequential type of processing, where parallelization is between processes and threads, but I'd say less native to this architecture. And the result is that if you take a bunch of data and you need to process it, obviously if you could parallel it by 2,000, if you like threads, versus 20, 30, or even 100 in some cases, obviously the 2,000 would scale much better. So it's really those things that I think lending or making GPU architecture, based architecture, lend itself better to that. Yeah, go ahead. Ilan, can you mute? Sorry about that.
Yeah, so
okay.
So something that's interesting too is, since I've been knee deep in the sort of machine learning and AI space, what it ends up looking like is very interesting. It looks very similar to traditional software. So, what's very hot right now is sort of microservices and things like that. And that's kind of what jumped the popularity of these event streaming platforms and PubSub, is because they needed something to coordinate all these microservices. But a lot of models are being deployed as sort of microservices. So it looks very similar. Now, from a DevOps perspective, this is where MLOps becomes sort of very important. And from my perspective, MLOps is basically the transition of traditional DevOps, but just focusing on ML. And that's why I'm sort of bringing up the parallels, because it looks very similar to traditional DevOps. But where it gets very complicated is typically most applications are linear in nature. It's sort of charging towards a future, and then it gets there, and then it's done, and then it sort of starts over again. But with ML and AI, Number one, those microservices, which are your model deployment. So after you've trained that model, it ends up being like sometimes like between 4 and 20 gigabyte file. That's what you get at the end of the day. It's just a single file that's massive. And then when you sort of deploy your microservice, it has to load that file because that's its intelligence. And the process of doing that is very difficult. So that can be like your microservice needs maybe 8 gigs of memory just to start up. So you can't sort of create a pod in Kubernetes inside of a Docker image and allocate, 256 megabytes of memory. Your service will never start up. Where this gets complicated is once that's sort of processed that file, and as the microservice that's doing the machine learning has quote unquote started up, it may only need 756 megabytes of memory. So you get into a very interesting situation where you have to allocate more for startup, and then you can pull it back. So there's just it ends up looking the same. There's just slightly different ways you need to do it. And also when you sort of get into what major companies are doing these days, they have hundreds of those. So whereas most companies or large companies have hundreds of microservices, AI and ML looks very similar to that. But those microservices are all models. And where it gets very interesting is you end up building a mesh network where model A, whatever comes out of model A gets fed into model B, C, and D. And then what comes out of model B, C, and D goes into other models. So it ends up looking like a mesh network that's sort of, they need peer-to-peer communication almost. So that's why the logistics in ML and AI is much more difficult than what exists today, which is typically built for things that are analytical in nature. Models.
Okay, so let's stop here again for just to make sure that we keep everyone in pace here. So MLOps is machine learning operation. It's basically DevOps practices for machine learning. The reason why you need something a little bit special for machine learning operation is the nature of machine learning is much more distributed, and it has all those aspects of shipping data as part of the DevOps processes, where I would say non-machine learning or typical traditional application, even microservices, are built in a relatively more stateless kind of fashion, where you process many application and services, and the data itself doesn't necessarily move with the application, and you deal less with the logistics of the data, that kind of, to pick on your words, around that. And the processes of moving data as part of DevOps processes, and includes all this pipeline of feeding, one thing feed to the other and feed to the other. That really requires a lot of that data shipping aspects that needs to be covered as part of that. So I think that's kind of what makes a machine learning operation an interesting challenge, and something that requires some more focus around that. So go ahead.
Yeah. And it gets even crazier complex because with machine learning, you're basically relying on something to sort of automate some part of your business. So it's giving some prediction, and you're doing something with that. You need a whole separate track of sort of sanity checks that go along with that. So these comes in all sort of flavors and all different things. So it's almost like when you build traditional software, you put in unit tests and functional tests and a CI and CD pipeline, all these things to sort of make sure that the code you're developing is doing what you expect in production. So you put in all these sort of safety things. So it's a very similar concept in machine learning. One big thing that's very dangerous is what's called like model drift. So that's where your predictions can be slightly off, and then the data is being fed back in through the system, and they're slightly more off. And so over time, they're becoming less and less accurate. If you're not tracking that, then you can get into a very dangerous situation where those predictions are hurting you. They're completely wrong, and you're driving your business off of it. So that whole sort of idea amps up the exponential nature of machine learning as well, because what that looks like is you're constantly sort of comparing the predictions to make sure that they're accurate. All the while, you're also developing new models to try to make them more accurate or maintain the accuracy. So that looks like you may want to pull 6 months worth of data and compare and run it through your new algorithm, your new model, and then compare that to what actually happened in your business, just to make sure like you've got the most accurate model, or to see if your new model is more accurate. So it ends up looking like the most complex sort of canary deploy of software, where you're slightly rolling things out to make sure things still act right from a traditional software standpoint. It's very
Even
similar.
though if you take the Biden versus Trump predictions, I'm not sure that those models are very accurate still. So we still have room to improve those models.
Exactly. And so, and the thing that's interesting, this is sort of depressing from my perspective, but due to the kind of position I'm in these days with Pandio, we work with typically Fortune 2000 companies, and the vast majority
let me again pause you here. We jumped into Pandio. Maybe why don't you introduce that period of time and where you chose to kind of move to Pandio, and what Pandio is, and what it is.
So in my sort of experience over the last 5 years, I sort of redeveloped and reinvented the wheel of data logistics. And when I was at Carpe Data, I saw a very clear trend with the major companies we were working with, that the existing logistics software like Kafka, Kinesis, and SQS was nowhere near adequate for what the future was going to demand. And so I started Pandio with a business partner of mine. He's sort of your traditional MBA. We've worked together numerous times, very good friends for the last 10 years, to sort of address that. We saw something that was alarming, and that was 83% of business executives want AI, but the sort of AI traction or who's using it is next to nothing. So we sort of wanted to help usher in that sort of promised future where AI is making everybody's life better. And I identified the sort of common denominator of logistics being extremely difficult as a big hurdle to that. And so having been running Pandio for a few years now, it's exactly what we see in the world. These large companies, without sort of naming them, they have a huge sort of problem with connecting data, getting it sort of in a way that they can do something with it, and moving past machine learning and analytics. If you imagine like what most companies are doing today from an ML and AI perspective, it's all analytical in nature. The majority, obviously there's, edge cases or people doing amazing things like Tesla's autopilot and things like that. That's very, very much way past just analytics. But traditionally, most of the companies are doing just analytics. So it's linear regressions, which is kind of, the basic form of machine learning. I view it as way far away from your traditional AI. AI is meant to be so much more than just linear regression. And so, the Biden polls and Trump polls and things like that, like those are traditionally just linear regressions. They're just doing kind of simple things against the data and making predictions on it. But when you move into sort of neural networks and things of that nature, that's like a massive leap forward in sort of capabilities. And the thing that people are struggling with is right now, the solutions out there like Kafka are bursting at the seams just for analytics. And to do proper ML and AI, which that's where I was knee deep in, it's orders of magnitude more of everything, more storage, more compute, more bandwidth, everything. And these softwares are already bursting at the seams. So that's where I sort of identified the issue of like, we're going to have a major problem. Like if someone doesn't come up with logistics software that can sort of handle that scale, we're going to be in trouble. So that's kind of Pandio in a nutshell.
Excellent. So what's the actual technology behind Pandio? What are you using in the stack there, and how do you actually solve that logistical challenges that you mentioned?
So one of the saving graces of my sort of experience in the past is I came across Apache Pulsar. So Apache Pulsar is basically an event streaming platform that can do pub, sub, and queues. So it has all the messaging patterns built into it. So it's really great. So I use that to sort of solve a lot of the issues I was having with Kafka and Kinesis and things like that. So we used Apache Pulsar as our foundation to Pandio. So we sort of took Pulsar and sort of made it better. So it's got stream processing and SQL against a stream, which is pretty interesting to write SQL against an infinite stream of data. But our real sort of value prop was, in all those experiences going back 10 years, DevOps was very difficult. So you had to throw a lot of bodies at it. And these aren't like low-level employees. Your traditional sort of highly skilled DevOps person, they're very expensive. So, some are $250,000 or more in salary every year here in the US. And we see companies in the Fortune 2000 that have hundreds of them, just sort of turning dials and knobs and things to keep systems running. So I saw an opportunity to use AI itself to improve that. So the big sort of benefit of Pandio is it has that sort of traditional messaging that can work for any sort of use case, but we use a neural network that actually runs our messaging. So it will sort of horizontally scale through Kubernetes. It'll reconfigure Pulsar and change sort of configuration settings, hot swapping them. So changing like caches and things like that, redistributing things. It completely runs it to the point where you don't really need DevOps. So in one of our biggest customer, who is a large public media company in the US, for this particular project, they had 15 DevOps people working on it. They switched it over to Pandio, and now there's a quarter of an FTE that's doing the same thing that those 15 people were doing. So it's really just an offset of DevOps because there's scarce labor there. DevOps, it's very hard to find good people there. And MLOps it's even more rare because it's traditionally like the cream of the crop of DevOps are moving to MLOps these days. So it's a very difficult thing that major corporations are dealing with right now, is scarce labor there. So our neural network sort of helps offset that. And the more data you sort of send through your messaging, the more value that neural network provides. It gets better. It sort of learns as it goes. So it's pretty fascinating.
Let me maybe try to summarize what we just described. So we're talking about Pandio and Pandio, right? That's how you spell it?
Yeah, Pandio, Pandio.com.
Right. So, and it sounds like you're really focusing on the part of the message processing of the machine learning, if you like, logistics, as I think you mentioned a couple of times. And on that regard, what you've done is really provided a message processing that has a machine learning engine behind it, that all the setup of how you configure it and tune it over time would be more automatic and wouldn't require any intervention of an engineer or a DevOps guy, and it will be self-configured, self-managed kind of thing, self-tuned even sort of things. And it's based on the Apache project. I forgot its name right now. Can you remind me again?
Yeah, Pulsar, Pulsar.
Right. Okay.
Yeah.
And why, by the way, did you choose Pulsar? What brought you to use it?
Yeah, there's a lot of different reasons. One of the biggest reasons, well, two of the biggest reasons was they unified messaging. So with Kafka, you can't do traditional queues. So like the FIFO queue that you mentioned earlier, Kafka can't do that. So if you wanted to sort of do the same things that Pulsar would do, you would need Kafka and something like RabbitMQ or SQS. So you need two pieces of software, just increases your tech complexity. So it has all three of those messaging patterns: event streaming, pub, sub, and queuing. And secondly, the biggest thing is it's cloud native. So it separates compute and storage. So if you want to scale up compute independently of storage, you can do that. So it scales much more easily horizontally. You can use more commodity hardware to scale out horizontally versus having to add more CPUs and more bigger hard drives, not more hard drives, bigger hard drives as comparison to Kafka, for example. So it's cloud native and sort of is built much for a container world. And that gives you a huge amount of flexibility to scale up storage independently, scale it down. So that gives you a lot of ancillary benefits like, Kafka, like I was mentioning earlier, it's very hard to get to 100% resource utilization with a Kafka cluster. With Pulsar, it's significantly easier to get closer to 100% server utilization. So, and there's just a laundry list. I would definitely invite people to check out their website. There's a huge amount of information there of all additional benefits like zero message loss. So it's designed to be more durable, which is great for the financial industry. We talked to a huge bank, third biggest bank in the world, and they were using Kafka, but they were noticing message loss. And so they had to build a whole other system to make sure that message loss wasn't happening. And they just had to do that because there's no other solution that they were aware of. So the financial industry has an especially hard time using Kafka. But if you can lose, 0.001% of messages and it's not a big deal, then, great. But when you're sort of ledger and transactions, that's a big deal. So, but yeah, those are the two biggest ones, but there's a huge amount. And we sort of took that as a very good foundation and built on top of it. So.
Great, and then the thing that you added is really the ability to auto manage it, auto scale it, auto configure it based on different patterns, as opposed to having someone in operation, DevOps guys that will continuously kind of manage the system, right?
Yeah, and we view it as a connectivity layer as well. So another thing we added to it is, for almost any ML or AI software out there, like Spark and things like that, we have connectivity into those things. So just if you're sort of doing an ML or AI initiative, it just saves time really at the end of the day. And the other interesting thing, we didn't get to talk too much about online machine learning. I think that's a really sort of hot topic that a lot of people aren't aware of, and they should be. If we have time, I'd love to sort of just touch on that.
Let's do that.
So, we were talking about sort of traditional training of models, and that's where you have to have a finite data set, have it in your hands, and then you do your sort of training, quote unquote, offline. So that's like you give a data scientist a really big box with really powerful GPUs and they do their thing. Online machine learning sort of flips all that around. So that's you sort of, as things are flowing through a stream, so you've got that sort of infinite data. There's no end to the stream. You're just getting data as it comes through. There's a library out there called scikit multiflow. So they basically took scikit, which is a very popular machine learning library, and then they turned it into online machine learning. And so that's why it's called scikit multiflow. So the idea is you've got an infinite stream of data. So as record 1 comes in, record 2 comes in, record 3, it's doing the training and the inference at the same time. Typically, those are not done at the same time. You do a whole bunch of training and then you do your inference after that and you stop training. And then you do more training after that a month later, and so then you've got a new model every month. So that means that every day that passes in the old way of doing it, your model's a day older and then a day older, and then which means the accuracy could be moving in the wrong direction. So with machine learning that's online in nature against an infinite stream, so there's no end, it's training with each data point that comes in. So that means it's as accurate as it's going to be at all times. It never is out of date. This is a lot easier in many respects because you don't have the whole MLOps apparatus of doing the training and sort of deploying the model into production. Your model's in production and getting smarter every single time data's flowing through it. So that's a very interesting sort of different way of sort of looking at that. And since we're so heavily sort of in that space, we're doing a very interesting partnership with NVIDIA with their Rapids framework, which is very much in this sort of space. So they're very interested in NVIDIA is very interested in stream processing in general. And this sort of falls under that umbrella. So it's stream processing, but it's doing a model training and processing, doing the inference on the stream of data at the same time. It's a fascinating concept because it makes everything easier. Your model's always up to date. You don't have the whole sort of expensive nature of pulling in 3 years worth of data and sort of training. Now, obviously, it's not a replacement for batch training because like I was describing earlier, when you've got a matrix and you need to be able to go forward in it and backwards, well, as you can imagine, in a stream of data, you can't go forward. There's no such thing as forward in a stream of data. You're always at the sort of, tail end of it. And you're limited how much you can go backwards just based on how much has been sent through it. So there's limitations, and some models require full forward propagation and full backward propagation, which means it requires a finite data set. So there's algorithms you can't use in this methodology, but there are algorithms that work in it, things like decision trees and things along that nature. So it's a very hot space.
Right. So okay, this is indeed fascinating. I just wanted to kind of make sure that it's clear when you use the simulation of the data and the training of the data, and when this real-time, I think it's called machine learning that we're discussing here right now is applicable. For example, if you're doing face recognition, you still need the all the pictures of the history of the person to actually do the recognition, right? So I'm not sure that will fit into that. But you said decision tree might be, so if you can elaborate on when that's applicable, because it sounds like too good to be true in the sense that, if that's sounds so, it makes so much sense, why are we even having other options of doing batch oriented stuff or, all the training processing that we've done before. Yeah.
So the negatives are definitely those algorithms. Scikit multiflow is a good starting point. They list the algorithms that you can do this with, and they also have a lot of examples that make that easier. The other thing is it takes a lot more compute to do online sort of training. So for example, when you sort of send that event through, and then it gets fed into the training algorithm, which is called like partial training, basically, its compute is about an order of magnitude more than if you were at that same point in an offline nature. So that's like an apples to apples comparison of online training versus offline training. The online training can be an order of magnitude slower, which is not necessarily a huge bad thing because, that's still, we're talking microseconds here. But if you design it properly where you do your inference and then you return back to the requester and then you do the training when nobody's waiting around, you can sort of offset that. But that is something to sort of keep in mind. It is slower apples to apples, but you can design around that. And then of course the limitations of the algorithms. I can't talk too much to those exact sort of differences. That's definitely where my data science sort of hits a wall on my expertise. Is I can't tell you the exact algorithm and the exact sort of reason, but it is almost always around backward and forward propagation. It's need to sort of look at more data than what's available in a stream. So imagine like a window of data. In a stream, you can say, you can look at like the last hour's worth of data, by sort of having a stateful function, and you just keep track of the last hour's worth of data. And then when the hour sort of eclipses, you do some calculation. But you're in a stream, you're not going to do that with like a week's or a month's worth of data. It doesn't really make sense. And surely not for years worth of data. That's sort of an anti-pattern to streaming. So anytime you need that for your machine learning, that's where the limitations are.
Got it. So that's indeed fascinating, and again, I feel that we can spend hours talking about that. By the way, my background in gigaspaces was really around solving large cluster data. In this case, it was kind of similar to what Redis is doing today. So gigaspaces was kind of one of the first in-memory distributed data processing, and I'm doing automation of in Cloudify of the automation of the processes of how you manage those things. So it's kind of touching those two aspects that I think you've mentioned in this call. One of them is the data logistics, as you call it, and the other one is the importance of the automation of the actual logistics part. So I think that fits nicely into my background on those two topics. One of the things that maybe if we want to kind of summarize and kind of talk about the and kind of close the discussion here is that I think there's a strong correlation when we talk about machine learning between, and I think you talked on a couple of aspects of that between automation and machine learning. So we tend to think of machine learning, as a more from a data science kind of perspective, but we tend to ignore the logistical aspect. And I think you kind of put a lot of focus in this call around that, which I think it fits well with the topics that we're covering right now. But you also opened another interesting idea of the logistics that can in itself use machine learning. I think that's kind of what you're doing in your company today, which is for solving the logistical problem, you could actually auto-configure, auto-scale, auto-heal your own operation by collecting the data and kind of remove or reduce a lot of the DevOps work that people needs to do today. So it's kind of looking at the logistic from a couple of aspects I think is interesting. And again, if to put almost final words around that, when we're discussing here this type of operational machine learning, you cannot really not think about those things because it's inevitable.
Yeah, and you know what, you're kind of touching on something that really pulls at my heartstrings is when I'm in a very fortunate position where I get to talk to the head of data scientist teams with major corporations every week. And, the sort of promise of the future where it's almost like imagine the singularity, or from the Terminator movies like Skynet, like those, where we're at today is so much in its infancy. It's not even close to sort of what that sort of future looks like, where it's more AI automation powering entire parts of the business. An entire manufacturing line is just completely automated. Today, it's more about making a human better, which like at their job, not in general. That'll always be true, but sort of future where AI builds AI. Imagine like AI writing software that does something, and then AI managing that software. So there's no human in sight. It just does what it does, start to finish. To me, that's like
a self-driving car. Or
exactly. Yeah. So if you sort of extrapolate that and imagine like if full self-driving was here today, it's one of those things where it's so almost unbelievable. Unless you like have a Tesla and you sort of see it do some things, you can like see the light. You can see like, oh my gosh, like we're getting there. It's not here today, but we're getting there. Whereas the vast majority of the companies are sort of just on analytics these days. And a lot of the very big companies are quickly figuring out that what they have today for analytics is nowhere near what's needed for what ML and AI is going to be in 3 to 5 years. It's not entirely new classes of software are going to have to be built. And so that's our sort of positioning is, what's out there is great for analytics. Our software works great for analytics, but that's not our focus. We're trying to help companies almost build the singularity in a sense. Like that's what we built for. We didn't build for a better mousetrap in analytics, but that's what gets me excited, is imagining a future where entire groups of AI completely solve some issue, and it's no longer even a conscious thought for humans. It's just AI takes care of it. We can think about something else and spend our time somewhere else. That's what we want to enable as a company, and that's the future I'm excited about.
Great. So Josh, thanks very much for taking you through this journey from your earlier entrepreneurship days on your, I would say, school or high school till today. Which I think covers a very nice spectrum also in the way data processing have started as, kind of ranking of websites. And you mentioned also the Craigslist as an example, to the point in which we're discussing this online machine learning, in which we're getting closer to this self-driving car experience. And as you mentioned, we're now at the stage of mostly analytics and less of that self-driving car, but we're moving closer to that self-driving car experience where it's going to be all the kind of closed loop type of automation. And that discussion kind of took us through that journey, both from a personal perspective, but also from a technology perspective. So hopefully the audience would appreciate that and enjoy the discussion. I definitely enjoyed it, and we're probably going to talk again next time. So thank you very much for getting into this podcast, Josh.
Indeed, thanks so much, Josh. Natty, also thanks so much, and also thanks to everyone for creating such a fantastic session. It was a really great deep dive. As usual, all supporting material for this session can be found at cloudify.co/podcast. And if you have any suggestions for future sessions, please feel free to reach out to us at hello@cloudify.co. We're there for you. In the meantime, stay healthy, safe, all the best for the new year and beyond. And we'll catch you next session.
This episode has been brought to you by Cloudify, the one platform you need to accelerate, migrate, and manage your multi-cloud environment for faster deployments, optimized costs, and total compliance. Head to cloudify.co to learn more.